today we are going to look at very important programming language abstraction, namely function or procedure. This is very important in the sense that you can build program in a hierarchical manner, in a top down or bottom up fashion, and without this constructing large programs would be impossible. The set of instructions we have already learnt is summarized here. This includes arithmetic instructions and logical instructions, which you see in the first two rows. When both the operands are registers, or one is register, one is in the form of a constant, comparison and branch, unconditional jump, load store, load upper immediate, and jump with register containing the address. So we use this as a means to jump to an arbitrary location, and also as a mechanism to carry out multi-way branch. As we went along, we also felt the need of some pseudo instructions, and some of the pseudo instructions we have defined are shown here. Move is something which is very frequently used, simply moving a data from one register to other register, essentially a copy of value is made. Load address, load immediate, which loads a constant into a register, and some variations of branch. Okay, these instructions are implemented by one or more real instructions. Okay, some of these we have seen how they get expanded, some of these we will discuss in tutorials. So today we will talk about what actually is involved in procedural abstraction. To implement a procedure, what all we require, what activities or what functions the instruction have to support. We will illustrate all this with an example. I'll continue with that sorting example which we had built up in the last class, and try to do in the form of functions there. And finally, we will find that there are registers which are although general purpose, but certain conventions have to be followed in order to develop a program smoothly. Okay, so what actually we mean by procedural abstraction? Essentially, procedural abstraction means that there is a piece of code which you can write once and use it one or more times, thinking of that as a single statement. Okay, so it could be an arbitrary piece of code which does a computation which has a well defined, well identified meaning, and this becomes your basic operation, either a single operation or a single statement, which can be used with the same ease and convenience as you do for the basic operations. So here it shows, for example, that there is a main program, there are two procedures P and Q, and P is being called here, this computation is performed, then there is a return which is made. There is another point here where Q is being called, and then there is a return. Similarly, P and Q are being called again, and there is a return. So the number of time we use could be arbitrary, and to implement this we require several things. Okay, several things have to be kept in mind. First of all, there is control linkage. You have to worry about flow of control. That means from main program you should be able to call, that means transfer the control, okay, in such a manner that when the procedure ends, the control returns back to the point where you made a call. Okay, so there is a linkage which is required. It is not simply a matter of using a jump statement one way and the jump statement other way. You need to know where you came from so that return can be appropriately made, because call may occur from several different points, and return has to be made accordingly. So that is a key part here. Secondly, every time you invoke a procedure, it may work on different set of data. So there is a concept of parameters of procedures, and when procedure is called, some data flows into the procedure. Okay, parameters are passed, and when computation is over, results flow back to the calling program. Okay, so the parameters which carry value into it, and those which carry value back to the caller. Apart from the parameters which are decided by the caller, or the result which are consumed by the caller, there are also often local storage declarations which you may have inside a procedure or a function. Okay, and if you call a function multiple times, then it's considered to be a fresh allocation of storage. Okay, so how do we handle that? At the same time, a procedure may make an access to the data which is defined outside. So there could be global data, there could be local data, and that both need to be accessible. In what I depicted in the previous picture was a very simple case where a main program and there is a function or procedure which is called, but there could be nesting. In the previous case, P could have called Q. Okay, Q could be called by the main, Q could also be called by P, and matter gets complicated further if there is a recursion. There could be a direct recursion or indirect recursion. That means P could have called itself, or P calls Q and Q calls P. Okay, so there could be direct or indirect recursion, and all these issues of control flow, data flow, organizing local and global storage become more complex when you have to take into account the need for nesting and need for recursion. So let's take the first thing first. How do you organize the flow of control? I am taking here the same example of a very simple minded sorting program, okay, where we simply had double loop, and the main operation inside the loop was comparison and interchange. So that comparison and interchange we suppose we define as a function or a procedure, okay, which I am calling as XCHG exchange, and now it is basically this exchange with some other overhead which is enveloped in two nested loops. Okay, now what happens at the assembly level? The rest of it is same. Okay, the only change is here. Earlier what I had done here was that although I had not shown in the same screen, but this comparison and exchange was basically a set of instructions, some 7-8 instructions which were placed here. Okay, now we don't place the instructions here, we put a call instruction, or which is called JAL, jump and link. JAL stands for jump and link, and I am treating XCHG as a label. Okay, so somewhere there is an instruction with this XCHG as a label attached, and the effect of JL instruction is to transfer the control much in the same way as jump instruction does, but it does one more additional thing. It saves the current address of instruction into a special register. Well, it is special in terms of functionality, but it's one of those 32 registers which we symbolically denote by RA, which stands for return address. So the effect of this is that $RA, or the return address register, gets the value of PC plus 4. So if PC is pertaining to this instruction, RA will now contain address of the instruction which is following. This is the point where you have to return after completing the procedure. Okay, so this address would be ready in RA register, and when you are done with the procedure, you can use that address and link back. So rest of it I have not changed, and here you can see how call actually has been established. Okay, now let's see what happens at the other end. So that what I called as the main step earlier, I have encapsulated in the form of a function here. Okay, so we are not returning any value, so return value is void. There is no parameter being passed. It's simply looking at global values and doing something with it. All right, so I've just added a return statement here. And in terms of MIPS language, this is the same piece of code. Okay, I've put this as a label, and at the end I say JR $RA. Okay, it's the same JR instruction which takes contents of a register and uses that as the destination or target address. So since JL had stored the return address in this register, you can simply do JR and get back. So these are the two instructions which actually provide control flow and linkage of caller and the callee. Okay. Now let's look at the question of passing parameters. Okay, we have seen how control is linked. Now we see how to take care of data. Now in this case, what I've done is from the previous picture, the only change is that I'm making P and R as arguments or the parameters. Okay, so the function need not look at values which were with the main, but it is explicitly passed on P and R, the 2 pointers, right? Now the way it is done, the simplest method is what is shown here, is use some specific registers which are designated for passing parameters. So the values which have to go into the procedure are loaded into these specific registers. So in this case, you can see $A0 and $A1. These are the 2 registers which are part of the set of registers from where I can convey the parameters. So all I have done is I have changed the register which I was using there. Okay, I was using something arbitrarily, but now I am just making sure that P is passed in A0 and R is passed in A1, and the rest of the program has been accordingly modified. Okay, so no extra statement. It is just that I am careful about which registers I have to use for this purpose, and typically I will avoid using them for something else. So what happens if you have large number of parameters? The convention is that if you have up to 4 parameters, there are 4 registers designated for it, which are labeled as A0, A1, A2 and A3. Okay, and actually that will cover lots of common cases. Similarly, the values being returned or the output from the procedure or function is through 2 registers V0 and V1. So once again, this would suffice for many common cases. What happens when the number of values going in or coming out is more than 4 and 2 respectively? In such a case, we have to resort to memory. So any additional parameters which you have, you can place them in specific memory locations, and the function is expected to load them from there, work with them, and the results can be partly returned through registers. If there are more, they can be returned through memory locations. So that's a simple extension of what we have seen through registers. Okay, the next issue was that of defining local storage. Suppose within the procedure, within the function, there is an array declaration or there are structures which are defined. So what do? You can organize each of the function or procedures with its own storage area, that is the data area, and the area where its code is kept. So for example, if you look at this picture, this is the main. Okay, this is green one is the data area, this is the code area. Then there is P, green is the data area, code area, for Q, data and code. Okay, so I have just placed them one after another in contiguous location. It is not necessary that data has to be before code, any convention you can follow. All that I am trying to say here is that each of the functions or procedure has its data and code together. Okay, another alternative could be that you have an overall data area where you keep data of each function or procedure, and then there is overall code area where you have code part of each function or procedure. So any of the convention can be followed, and of course a compiler would follow always a specific convention and produce the code accordingly. So it will process all the procedures, they look at their code part, look at their data part, and do storage assignment accordingly. Now let's move to the case of nested calls. That means a function can call another function. So, I am showing here an example where this is the main, okay. At some point you are calling function p, okay. This is p, and there is some computation here, somewhere you are calling q, and this is q. So, this is the return point of q, this is the return point of p. How will they appear in assembly? You have JLP for this call, so that will bring the control here, and at some point you say JLQ, the control gets transferred here, okay. Here you expect that JR$RA brings you back here, go further, you expect that JR$RA brings you back here, okay. So that is how you want control to be linked. But now what will happen? When first call occurs, the address of the instruction here, which is after this JL, gets stored in RA, okay. But when you reach this point and issue another JAL instruction, then the old address which was there in RA gets replaced by address of the instruction following this, okay. So there is no way you can return to the main, and here this call will occur correctly, this return will occur correctly, but after this point again when you say return, the program will get back to this point. So it might get into an endless loop here, and the solution is very simple, that you must take the precaution that the return address which was made available here should be saved somewhere, and before you do JR it should be restored, okay. So now this procedure would have some local storage. To that you can add one more location where it preserves its return address, alright. So now in between many calls can occur, Q can call something else and so on, but as long as P takes care of where it has to return, the job would be done, you will not make a mistake. So Q can take care of saving its own. So what you could do is the first thing when you enter a procedure, you save the contents of RA into some memory location, and just before call, the last thing you do before returning, sorry, not before call, just before return, the last thing you do is from that memory location load into RA, okay. So once you have done that, in between RA is free, you can make any calls, you may or may not make a call, okay, and there could be any nesting of calls. So here is an example. What I have done is that in that sorting case, sorting problem, the inner loop has been redefined as another function. Okay, you recall that it was trying to find a minimum and put it at the right place, okay, minimum of certain number of elements. So it was being passed as it's being passed as two parameters, P, which is the pointer to place where minimum value has to be kept, and R is a pointer to the area in array from where you need to start scanning. So R is made P plus 1 and then you make a call, okay. So what min will do is it will go through that loop, go through a scan of the array from R onwards and bring the minimum element back to location pointed by P. So rest is same, and now we are left with a single loop here. So there is a single loop call to min. Min has that inner loop basically, okay. It performs that exchange conditional exchange, compare and exchange, update R and keep repeating, okay. So this is as it is, this I have not changed, this is the innermost activity which you do, compare and interchange. Let us see now how these will be done, each of these. So the main body, we have simply JAL to min, okay, as a replacement for this, and we are making sure that the two parameters, okay, there is a mistake here, there are two parameters P and R. So I am making sure that the two parameters are in A0 and A1, so that both caller and the callee understand where the values are to be looked at, and this is the call to min procedure. This is the same min procedure, and this is how we have implementation. So I have added these two instructions here, right. Apart from that, it's a simple loop. This is the same loop, makes a call to exchange, updates R, compares and goes back. So this is a simple loop here, and that basically forms the body of this function. All I have done is I have actually padded up with save and load here. So here I am saving array value into this location, and I am loading it into this location. So now please notice here that I have used this load and store somewhat like a pseudo instruction. Okay, I am not worrying about whether this address called array save is a small constant or a large constant, or how it is to be handled. So I am just leaving it as it is. Assembler will translate this into possibly two instructions, okay, or two or more instructions, which will prepare the address into a register, and then with the suitable offset it will use SW or LW instruction. So again, elaboration of this we will see separately, but all that we need to understand here is that array is getting saved somewhere, and from the same location array is being restored. Okay, now let us move a step further, okay, and go for what is called recursive call, which means a procedure directly or indirectly called itself. So there is a cycle which is formed, and we have basically changed this loop which was inside min into recursive calls. Okay, so it does not, it's not necessarily just, it's not necessarily improving the program, but just for illustration I have rewritten as a recursive call here. So if R is less than or equal to Q, instead of saying jump to exchange, okay, I am saying make a call to this function, and meanwhile the value of parameter has changed, R has changed. So you will keep on calling this and return when you find that this is false. Okay, when R exceeds final value, then you start return, and R is unchanged, so you will keep on returning, keep on finding this false, and all chain of returns will happen. Okay, so is it, are you able to follow this program? Right. Now let us see its translation in MIPS. So I took care of saving this and restoring this, right. Earlier I was making this comparison and looping back. So instead of looping back, I am making a call to min again. Okay. Now the parameters I am maintaining in A0 and A1, so I don't need to do anything else. I simply make a call, and I am hoping that the control will repeatedly enter this and appropriately exit. Now what will happen if I do this? Where do you see the problem?
RSA will be the last value of the
Yes, I am every time I am saving array value into same fixed memory location, right. So first time the value which gets stored is the value corresponding to call which came from outside. Subsequent calls are getting generated inside. So subsequent returns are to this point. You see here there is a call, and the return takes place here. Okay. So these the every time now return will take place here, because the original entry point from outside has been lost. So the solution of this is that I should not lose any value which is saved, and in natural structure, natural data structure, where the value can be saved is a stack, which is a last in first out structure, because the order in which calls occur and the order in which returns take place are in a last in first out manner, and therefore as I enter into function from wherever call is occurring, the return address gets pushed in a stack, okay, and just before returning I pop the latest one from the stack and use it for JR instruction. Okay, so irrespective of how calls are occurring, whether it is nesting of calls to different procedures, or there is recursion to same procedure directly or indirectly, you can simply keep on pushing the return addresses into a stack. As soon as you enter a function, push the return address into stack, and just before exiting take it off from the stack and return. So now the question is, how do you do this? There are no direct instructions in MIPS available for pushing and popping. The stack is created basically by using a special register called stack pointer. So once again it is one of the 32 registers which is used to implement a stack. So pictorially, let us say this is the stack, and conceptually you can make stack grow towards reducing addresses or increasing addresses. So I am imagining that let us say address 0 of memory is at the top and maximum address is at the bottom. So somewhere I define bottom of the stack and start building stack towards lower addresses, towards 0, and this register SP will always point to top of the stack. So for push, what I need is that decrement the stack pointer to create space for putting in data, and then store the value you want to put in the stack. So add immediate SP minus 4, then store word RA at SP. Now one more thing I like to notice, this is just a side observation here, is that with add immediate also the constants can be positive or negative, okay, and actually it is because of this reason there is probably I had listed subtract immediate as an instruction, but actually there is no subtract immediate instruction. You add immediate with a negative constant is nothing but subtraction, okay. So here you are subtracting 4 from stack pointer, and pop is just the opposite. So you pick up value from the stack as pointed by the stack pointer, put it in the desired register, and update the stack pointer, increase it by 4 so that the value is no longer considered to be as part of the stack. So these are the instructions which you would use to save and restore the values of returned address. Okay. So this has taken care of the control flow in a recursive environment. All right, we are ensuring that information about return doesn't get lost. What about data? So when you're passing parameters in a recursive call, in the previous example, situation was simple, that after the call, when I return back, I don't need those values. Okay, so basically every time a call is made, the fresh values are passed on, and what happened to old value I don't have to worry about. But you could have a situation where there is some code after a recursive call also. Okay, so you passed on values P and R, but you are still working with them. You need to do more operations. So in that case, you cannot afford to lose old values, and the right solution again is use a stack. So the parameters could be passed through registers if situation is simple, but if you need parameters to be available even after the nested calls, old parameters, you need to keep them in the stack. So you can save the parameters, or you can pass the parameters through stack. Okay. Also recall that I mentioned that if number of parameters is more than 4, you use memory locations. So now that question also gets answered, which memory locations. So additional parameter you can simply push in the stack. Okay. So before you call, you load the parameter in the stack, and when you are inside the function, you can take it off the stack. Stack is also used for allocating the local data. So now imagine that you have a recursive call to a function which has its own local data. So it means for every occurrence, for every instance of the function, a new array has to be declared. Suppose there is a local array, so with every call a new array has to be declared, and they cannot be all located at a fixed address. Once again, the natural place for them is stack. So over on the top of the stack, when you enter a function, you can earmark space which corresponds to your local data. So you can create your local arrays or all local structures at the top of the stack, and before you exit, you can clean up that area. Okay, so it's no longer required. Okay, one more problem one has to pay attention to when talking of procedure is that when you are writing a program, you assume availability of certain number of registers, and you may freely use them, but when a call occurs, the control is getting transferred to a function, okay, which will again require registers for its own computation, and when control comes back to the main, the main program will continue with the computation which was done partially. So some intermediate results may be available in the registers, and if you are not careful, you may conflict. Imagine a situation that main program is written by one person, one programmer, and the function is written by another programmer. So either they write in sequence, once A finishes, tells that I have used these registers, you go and use other registers, or there could be a fixed division. All right. So there is a convention which can be followed, which is the task, and if necessary, you save the registers. So if let's say you are writing the calling program, you have done partial computation, some results are in the register, you need to make a call and then come back and continue. So the values which you need to preserve, you have to take care that you save them. Okay. So whether caller should save or callee should save, again a convention helps in this area, and this question this conflict will not be there. Otherwise you would write programs, two people will write program, there will be a conflict, one would destroy the value of others, and then fingers will point to each other. So the convention which is followed here in MIPS is given here, that registers S0, S1, S2, etc., these are called saved temporary registers. Okay. The caller can assume that it is safe to leave values in these registers, and everyone has to ensure that values of these is preserved across calls. So if some partial results were left in S registers, you can be safe if everyone is working, if everyone is complying with the convention, then you can assume that values will be retained. And if callee feels the necessity of using registers, it will be made in a very transparent manner. So it will save the values before using, save the caller's value which were left in these registers before using, make use, and then restore those values. So as far as caller is concerned, caller will stick to that assumption that value in these is not disturbed. If it is disturbed, it is done in a manner that you don't come to know of. Similarly, registers T0 to T9 are called simply temporary registers, where values are not expected to be preserved. So callee has no responsibility of leaving these untempered. Okay. And on the other hand, if caller requires these values to be saved, okay, if it needs more values than these 8 to be saved across calls, it can put in these, but then there is no guarantee. So if there were values in this, caller is expected to save them somewhere safely, then make a call, and when you come back, recover these values. So these are not preserved across calls, and they are saved by caller if necessary, right? So these conventions define who has what responsibility, okay, in terms of tampering with the values or touching the values, and saving in case if it is required. So now all put together, we have been talking of lots of register names, and there is some convention. In some cases there is hardware constraint. So here is a summary of all the registers which we have talked about. So starting with 0, okay, this is ensured by hardware that the value is constant 0 in this. Okay, there is one thing is missed out here. $80 is register number 1. Okay, it was assembler temporary, which is used for expanding pseudo instructions. So when expanding pseudo instruction requires a temporary calculation, for example preparation of address or storing the comparison result, then assembler uses $80, okay, or register 1, and programmer is expected not to use that, because if you use it and at the same time you are also using some pseudo instruction, you can run into problem. Then the next few are for parameter passing. V0, V1 are basically number 2 and 3. They are used for returning values. A0 to A3 are passing values into the procedures. So they are numbered 4 to 7. Then we have T0 to T7. These are temporaries. S0 to S7 are saved temporaries. For some reason T8, T9 are not contiguous with these. Then there is a gap. There are some registers which are used by kernel, again they are reserved. Then we have global pointer. So if you have global data, okay, which is shared by many functions, many procedures, then that could be in some contiguous area, and a register GP could be made to point to that, and with suitable offset to that register you can access various components of the data. SP is the stack pointer which I talked of, RA is the return address, and FP is frame pointer. I will describe its use shortly. So these are the names which you can conveniently use. Internally they are $0, $2, $4, etc., and that's the usage. So hardware wise, it is ensured that register 0 has certain value, and JAL instruction assumes that value is to be put in RA. Okay, others are by convention. Okay, so the fact that we are using these for parameter passing is only a matter of convention. The hardware doesn't know this. Similarly, that the convention about these, about T's and S, is again a convention, and hardware doesn't understand this. Stack pointer is again a convention that we are using this particular register for pointing to stack. Anyone can be used. Okay, once again it's a convention. With RA there is a role of the hardware, in the sense that when you execute JAL instruction, the return address is put in this particular register. Okay, the return instruction, the JR, is a general instruction. It's not specifically for return. We have seen other usages of it. Okay, finally I'd like to show you what is called an activation record or a frame. We have talked about putting so many things in the stack. Okay, once you come to recursive calls, then basically everything, the solution for everything I mentioned was stack. So all this information in the stack is organized in a particular manner, which is again a convention, and different systems may follow different convention. So what is typically followed is shown here. So every time a function or procedure is called, you create an activation record on top of the stack. Okay, and when you return, you clear that off. So as nested calls occur, you build these activation records in the stack, or these frames in the stack, and typically the stack pointer will point to top of the activation record, and other pointer which I mentioned, other register FP, is called frame pointer, points to the beginning. Okay, it could point to the first location here, or maybe the last location of previous activation record. Again, convention could slightly vary. So I have tried to put almost everything which I discussed earlier. The arguments which are being passed on would be one part of this record. The return address which is to be saved is saved here. Any S registers which you need to save, they get saved here. Local data is allocated here. So this whole thing is the frame. So a function basically works with this. Okay, this is what it sees as local data area, and apart from this, it may make reference to some global data. So it will use that will be accessible through GP pointer. So through GP, FP, and SP, access is made to all the data within a function. Now the question would be why we are having two pointers, SP and FP. So one might imagine that suppose you have a pointer either here or either to the bottom or to the top, everything could be referenced in terms of some suitable offset from this point or that point. Okay, but there is a difficulty in that, particularly when the size of this changes dynamically. Okay, if within the function you are doing any dynamic storage allocation, okay, we have not seen at assembly level how you do that, but suppose the program is sophisticated and dynamically allocation gets done, so this moves up. So now this can no longer act as a reference point for accessing the data, because we want the offset to be constant. Okay, typically the way you like to access is load word, some constant offset, and maybe register in the bracket is SP. So with respect to this pointer, the offsets are for these are constants. Okay, but with respect to this pointer, offsets may not be constant. We need a pointer to this top to keep track of how far the stack is filled up. So that is required in any case. But another pointer here, so that all these can be accessed with a constant offset, is required. Okay, so let's summarize. Let's close at this point. We have seen some of the basic ideas of how we create procedural abstraction in assembly language. First issue was that of arranging procedure call and return. Then we saw how parameters are passed. We talked of the complications which arise because of nesting of calls and also recursion. The solution was to follow a lot of conventions and also to use stack for all storage allocation. So with that we have seen the basic idea. I would, in the next class, I will take an illustration and show how a complex recursive procedure can be programmed, where you need to do activation record creation. I will stop at that. If you have any questions, I would answer those.
Can you explain frame pointer again?
Okay, yeah, frame pointer. The basic idea here is that we have all the data allocated on the stack. Okay, if the data was of a size which is fixed when you are writing the program, then every piece of data can be accessed with a constant offset with respect to top of the stack. Okay. But if situation is different, that means let us say there is some data structure, maybe you have prepared there is a local linked list, for example, where the size may grow or shrink as the function proceeds. So all that allocation of the linked records will be on top of the stack, and therefore the top of the stack will keep changing. So stack pointer can no longer be used with constant offsets to access, for example, these arguments or the return value or these registers. So we have a pointer to the bottom, and with respect to that, the offsets of all this part is constant. All right. Of course, the access to the dynamic part will be changing, and it will not be accessed in the same manner. For that, we would need more complex methods, but at least the part which is unchanged, whose location or seat is unchanged during the life of the function, we can simply access by a constant offset to the frame pointer. Okay, there was some question over there.
So when we did stack pointer initially, so you said we push and pop the various return addresses.
Yeah.
So in that, it won't be happening that we are pushing all the addresses and pop is happening only once.
Yes, actually, in aggregate terms, the pushes and pops have to match. Okay, so you might push different things in pieces. For example, you may push arguments, then you may push return address, then you push registers. So several instructions may be used, and stack pointer may be made to grow in many steps. Now when you need these things, you can use them, and you may clear off activation record in one go, or again you may do it in parts. All you have to ensure is that the space which was allocated should be equal to the space which gets deallocated eventually. Okay, so these have to be matched. In fact, this could be one very common source of error. If your pushes and pops don't match, there could be serious problems in the program.
So how much memory is allocated to stack pointer?
How much memory is allocated to the stack pointer? Okay, the memory allocated to the stack pointer, stack pointer is just one register. Okay, so your question should be how much memory is allocated for the stack. There is often no fixed memory may be allocated. You may start at let's say one end of the memory and allow this to grow in one direction. Okay, sometime you have let me okay, often you may have in your entire memory, you may have this is a very typical case that you have two data areas which grow in opposite direction. Okay, one is called heap, other is called stack. So, for example, if this is stack, it grows in this direction, grows and shrinks. Other could be heap, which grows and shrinks. So, heap would be used for random allocations, for malloc and so on, and this stack is used for automatic allocations when calls and returns happen. And you could actually, what you could do is you may make a fixed partition and say that above this is the area for heap, below this area for stack, but that may constrain. Sometimes you need more stack area, less heap area, sometimes you need more heap area, less stack area. So, a common policy is to not have this line, okay, and let them grow freely, so that total space is available. As long as they don't clash into each other, your program works successfully. So, if it does, then you run out of memory. Okay, so I hope I have answered this question of how much space you allocate. So, you may often not allocate a fixed space and leave it to grow or shrink dynamically. Okay, thank you.